I'll give the first part of this presentation, and Antonella will jump in at the last bit for some latest developments. The presentation is about data standards, so building on the presentation of Ilya and continuing towards visualization that we'll be using later during the practical exercises. First, the overview. Well, as I said, using standards, then first a few words about using standards in general, and maybe I'll say something about what's good standards and what's bad standards, although Ilya recommended against saying good or bad about standards. But and then I use that to say why we chose certain standards within the DRIHM project for the infrastructure. And then secondly, we'll talk about visualization tools, and first the offline tool that we'll be using mostly during the exercises, and then the visualization tool embedded in the DRIHM portal as the last topic. Well, first, the models, some of the models have already been mentioned, but this is kind of the picture of the models that we were thinking of when we started the DRIHM project. Meteorological models, hydrological models, hydraulic models from different origins. So how would you go about in coupling those and passing data from one to the other? Well, you start saying, okay, well, I can pass data from one model to the next, but then at a certain moment you are building a lot of conversion routines, and it's a big mess and a lot of time. You spend more time on writing converters than on doing the research and the science and focusing on the processes you model. So that's not a proper way, so we said, okay, what's the life with standards? So how do we go about? Well, we decided to identify a couple of interfaces, and you will see this theme reappear later during the sessions. And okay, if you have a WRF model, two meteorological models nested in each other, then that's specific for those models. We don't want to interfere too much with that. But then at the other places, we have tried to come up with standards. And I try to identify them here now such that I can explain a bit more later. So we have introduced a P interface. Remember P as in precipitation for information that goes from basically the meteorological models to the downscaling models, and from meteorological models and these downscaled models in general to hydrological models. Then we introduced the Q interface, the discharge interface, for which we are using WaterML file between the hydrological models and the hydraulic models. And here in the interaction between hydraulic and impact models, we're going to use the OpenMI interface. We'll talk more about that tomorrow morning and afternoon. And the OpenMI interface will allow a two-way coupling, whereas the other interfaces that we are using are file-based one-way couple. So one step is introducing these interfaces. The second step is making sure that the models use those standards. So within every box, you should think of not just the model engine, but also the conversion from the standard interface to the model specific input, and from the model specific output to the standardized interface. So, well, the first slide already indicated a bit why we would think standards are useful, but okay, let's go in this direction a bit more. So standards are useful because they simplify the data access. If you use a standardized file and others are using the same standard, otherwise it's not a real standard, you can get easy access from different programs to your data files. So, it's easy access is the first thing. Easy data exchange. If you're using the same file format like a Word document, I can give it easily to somebody else, or PDF is even easier. I can open it on my cell phone and these days. So you can go very easily rather than having every word processor having its own file format. And then easy comparison. As yesterday in the presentation by Olivier, you start to, if you get models from data from different sources, you can more easily integrate them and do an analysis. So switching to a standardized file format, yes, it will cost a bit of time, or some, depending on how complex your system is, more time, but a bit of time initially, but it will save you a lot of time later on. So, but then the question becomes, what should I take as a standard? So it's good to use a standard, but what do we accept it as standard? And well, obviously you should not trust somebody saying, okay, this is a standard. You should all use it, because, well, is the rest of the world using it? Unless that's the only person you are communicating with and you're fine with that. Otherwise you would prefer to have something that is more widely adopted. So there are basically two ways that standards can develop. There is a top-down approach, national standardization bodies or international standardization bodies. Well, what happens if you take a national one? Well, you get a standard plug. Yes. So every country has its own standardization body. So doing something at a national level might not be the right level in this day and age. So international standardization bodies is a better bet, although they don't solve these problems that easily. The other option is following a bottom-up approach and getting together as a community and saying, okay, what is what we need for our daily work? It's more practical, but yeah, there are also some issues. So the international standards tend to be slow in development. A lot of people need to agree, and it's viewed from a lot of different angles, and the resulting standard might be very complex. However, if you take the bottom-up approach, you agree with your colleagues, but somewhere in another country, like the national standardization bodies, they come up with another standard, so they are not as standard as you would think they are, or you hope to be, and you have possibly a domain bias. So what I would phrase here as what would be a good standard is a standard that's developed by a community, because it's solving the issues that they need to be solved in the most pragmatic way. But if they get approved by international standardization bodies, that means it needs some maturity. It's not just that group that found it useful, but there is a wider, and especially if it's an international global body that confirms the usefulness, then it's a signal that it's a good standard. So for DRIHM, we chose 3 standards as the interfaces. We chose the WaterML2 standard, the NetCDF, the CF standard, and the OpenMI standard. And basically all 3 went through this process. a little bit more about WaterML, then something about NetCDF, and OpenMI we'll be talking about tomorrow. WaterML2 is an XML storage format, as already presented by Ilya Saslavsky. The first versions were developed within the consortium for advanced hydrological sciences, QASI, and it took, I think, 5 years for that standard to further develop into a version 2 standard, which is now within the OGC. So even the acceptance by international body is sometimes a slow process, but that's because you open up to a wider community and double check whether you have made all the right decisions for all the right reasons. Saying, well, it's coming from a community, and even though you opened up to a wider audience, there's still domain bias. WaterML was identified as a very useful standard, but why call it WaterML? It's more about storing time series at certain locations, and it doesn't have to be water specific. So that's why you see, okay, it's a useful community standard, it's growing to maturity, but still there are ways to improve it and make it more general. Within DRIHM, we restrict the use of the WaterML format to only one discharge per file. So if we are looking at ensembles, you will have multiple files. If you have multiple output locations, discharge locations, you will have multiple files. We did that because it makes it easier for the DRIHM infrastructure to manage which data needs to go to which model. If everything is in one bulk file, you need to reprocess the files. So we chose this option. Ilya already mentioned a couple of things about it. The file format, I will highlight a couple of more aspects without going into the details. Basically, a WaterML file, in the limited sense by the DRIHM project, contains some generic information about when the file was generated, by which model. Then we get a block with temporal extent, specifying the time range covered by the data in the file. It has a label, so you will see a couple of these labels popping up. There's one here as well, but it's not as, we'll not refer to it later on. Then we have a block referring that will be using the word river discharge as defined within the DRIHM project, so it's vocabulary. In the end, you want to refer to river discharge as in an international standardized vocabulary, but for the time being we've selected a local one. So we define river discharge, and then we have a location definition, as Ilya already mentioned, using GML encoding, and that identifies a monitoring point. So when we then come to the data, we refer back to the data, saying, okay, this data is for this time period. It concerns the river discharge as defined before, and it's defined at this monitoring point defined before. And you see that, well, you could have multiple of these data blocks in your file, but we chose to have only one per file. And so we then continue with the actual data values going down in the file. It's an XML file, so it's a bit verbose for reading by a human, but it's pretty easy to parse. So switching to NetCDF. take a little bit of a different scope here, say, okay, why NetCDF? NetCDF is already, you can access it from all these files, from all these programs, and there are even more. So in general, it has already great community support. But it was also recently adopted by OGC, NASA and others are also using it. It's used for IPCC reports. So there is a very broad acceptance of the standard. So also community-driven, great amount of data tools available and formal approval by standardization bodies. So what's a NetCDF file? Who has not worked with NetCDF before? Okay, a few. So it's great, the majority already knows NetCDF. So I can go through this pretty quickly. So NetCDF is basically, as NetCDF file format, it's just basically a container, like a Word document. Word document contains text, but if I open the file, I can see that it's text, but if it's in Chinese, Spanish, English, it depends on the language whether I am able to make sense of it. So there are blocks with data. So what does the data represent? The NetCDF file format does not say that by itself. NetCDF comes in basically two main flavors. NetCDF 3, then it's really a file format, like the Word doc file format, and the NetCDF 4 file. Well, it's not a file format, it's actually HDF5 file format extended with a NetCDF layer on top of it, with an access layer. So it's somewhat more like a docx file format of Word. If you've used it, actually it's a zip file containing all kinds of other simple files. So the HDF5 is then the basic file format, but NetCDF adds something to it. What does NetCDF add to it? NetCDF adds labels for the arrays. Well, by themselves they are not that informative. And it adds labels for dimensions. And then you can start seeing, okay, well, these arrays share spatial or some dimensions. They may have some relationship. It's not just arbitrary arrays that are stored in this file. It also adds ways for adding metadata. And that's where we continue with the CF metadata. The CF metadata, CF stands for climate and forecasting. It was developed largely within the context of the climate modeling community. And what it adds is elements like spatial coordinates, definitions. How do you do that? If there is a one-dimensional array which has the same name as the same name for one dimension as it has for the array, then it's a coordinate. And well, there are other things for two-dimensional coordinates and auxiliary coordinates and so forth. So you can start making sense, okay, if this is longitude and latitude and that correlates to these arrays, then most likely these are spatial arrays. Also temporal coordinates are identified, not shown in this picture. Then we have things like standard names. It's a little bit of a mixed feeling. Coming from the climate side, they tend to have big names like sea surface elevation. That's when you look at the climate, all the relevant water levels that you're looking at. But if you're going upriver, it's not what you would refer to as a sea surface elevation. But then again, where is exactly the transition and how do you name it? As long as it's a standardized name, it's fairly easy to make your own translation to whatever name you want to use in your system. and then units and other metadata standards. So you then see, okay, I have here water level, I have here the depths, I have two components of velocity, so now I can start making sense of the data. So that's the combination of NetCDF plus the CF conventions for data storage. Now going back to the DRIHM infrastructure, we talked about the P interface being stored in this NetCDF CF file format. For that, we selected a couple of standard quantities. And these are the quantities that you will see when you open this afternoon a NetCDF file in one of the visualization packages. There are a couple of quantities, LWE thickness, which stands for liquid water equivalent thickness of precipitation amount. It's basically the amount of water, if you would collect the amount of water you find in the rainfall tube. It's the thickness, the amount of water per square area, the thickness of that of the rain, and then it's also the total thickness, and then for meteorological models making a distinction to what type of meteorological phenomenon created the rain. Then we have air temperature, specific humidity, an energy radiation flux, the wind direction, and the surface pressure. And these quantities have been identified as quantities you typically would like to have in your hydrological model, or possibly if you start coupling it to maybe an ocean or an open water model for a lake or a sea, what kind of information do you need for the energy balance and for the forcing of the flows in such bigger water bodies. So that's where I stop with the standards and switch to the visualization tools. We'll have 3 visualization tools mentioned, I believe. First of all, the standard standalone tool, go more into detail on that one. Then the NetCDF visualization tool in the portal, and then later on today Fabio will show something about or will guide you through a drift model, or he showed it already yesterday. I think it was a Python routine for visualizing water ML2 data. We'll not go into this one here, just the top 2. For the standalone tool, we use Delft3D QuickPlot. It refers to the Delft3D hydraulic modeling system. It was originally just a visualization tool for that package, but it has been extended to use also for other models. It's coded in MATLAB. It can be compiled to run as a standalone tool, but since we cannot install anything on the local machines here, we'll run it for this course here within MATLAB. For those of you who don't know MATLAB, you don't need to know much about MATLAB during this course. If you start MATLAB, it will show you a command prompt area, a list of files in the current folder. If you start developing and programming things, you will see variables appearing and history of executed commands. And you see in the top, you see where you are located in the operating system and the current folder. All the things, the things that you need to know is you need to be able to type a cd command to a directory, and I think there is a zip file in the same location as where the virtual machines were yesterday, containing a file quickplot within MATLAB. You unzip it and go to the directory where you unzipped the file. If the directory name contains spaces, you may need to make sure that you put the directory name between quotes, otherwise that's not necessary. And then you type quickplot. That's all about MATLAB you need to know today. The rest is going through the GUI. This is the main window. The things we are going to use is the file open menu and file open button to open a file. Could be a netcdf file, waterml file, maybe some ArcGrid files created by other components. And we may want to look at the plot manager, which is either this icon or window show plot manager. If we go to files and then preferences, we can select which files are used in the file open menu. Quickplot can open a lot of files. It's by default it's configured for the Delft3D system, so we might want to change it here slightly to have file filters for netcdf and waterml2 files. So it's also in the handout or the guides that you've got how the steps describing how to filter those. Then if you press the file open, then you will see in the lower right corner, you will see a selection of the file types, and you can say, okay, I want to see netcdf files or only waterml files, and that helps you to navigate through to the right file. In the end, it doesn't matter which file format this file filter is selected in the lower right corner. If you just select star, enter, and then you can see anything, you can change your file filter. It will automatically detect from the file contents what the file format is. So, very quick overview how to work with quickplot. Once you open a file, you will see the file name in the top left corner. You can open multiple files and switch between files using the list box here. Then per file, it gives you the quantity stored in the file. So we see the LWE thickness of precipitation amount here listed. It will indicate the number of time steps. If you check the box show times, it will show you what the dates are. Since sometimes you have a lot of dates in the file, by default we don't show it for performance reasons. And then you can have a spatial selection. It will identify an M and an N direction, and you can, by default, you will probably here keep both dimensions selected, but you can also make just a longitudinal slice through the data. Basically, if you're happy with this, you can press plot or quick view. But you can tweak the plot by going through the right column and changing color schemes and plot options like continuous shades or patches or contour lines. You can also specify clipping values, which we'll address a bit later on. And so if you then plot it, you will get a plot like this. Since this is the last time step in the file, it has an automatic scale for the color bar, and you can either use the lower left a scroll bar in the lower left corner of the figure to scroll through time, or you can press the animate button and loop through all the time steps. This is bit overwhelmingly blue. Maybe we can clip all values that don't have rain. So we then go back to clipping values and add a 0 over there. And then it becomes already much clearer where the rain is located, but still we don't have any idea where this is. So for that we need to go to the plot manager. So we can go back to the main window and select plot manager from there. And then we'll have this window pop up, and the last icon in the toolbar, it will allow you to add some geographical information to the plot. The top 3 are local data sets, provided the files are provided with the quick plot. The other files are downloaded through the web mapping service, as already referred to by Ilya. But you need to have an internet connection, so be aware that if you have a virtual machine running, you may not be able to use the bottom options because it cannot access the internet. So still the top ones are possible. Yeah, so if we take the previous plot and add the shorelines, we can see that lots of rainfall in southern France and Italy. So we are back at the November 2011 event. And if you add the Bing maps to it, you can get a more nicer geographical information on where the data is. So that concludes my part of the presentation almost. There is a manual. From the help menu you can access the manual. It's also available on the OSS Delft 3D website. You can go to download manuals and then select the QuickPlot user manual. Well, this link is also specified in the document that you received on the summer school. So I'll now give the floor to Antonella.
Give me also the mic.
Yes.
Okay. As Bert has kindly introduced for us, we have the possibility to exploit visualization services that is being developed inside the board. So, we have these online visualization services that is able to visualize netcdf files that are remotely located. And these files are associated to the P interfaces, as we just said. And what I want to do with this 10 slides that I have is to make you familiar with this tool. Thus to be able in the afternoon to exploit it if you have pleasure. And so the visualization tool is based on NCBWMS, that is again a web map service, again this name, that visualizes for geospatial data that are stored as CF compliance, so netcdf compliance files. Again, a web map service is an HTTP interface for requesting images that are geo-registered maps that can be stored in database that are more or one geographically distributed. The tool itself has been developed at the Reading University at the eScience Center in UK, and that is the link to the tool itself. We provided a portlet that integrates this tool, and you can use it without your grid certificate. Probably this is a good news for you. You don't need the certificate to work with this service. And we pre-uploaded on the portal most of the output you saw yesterday in the talk from Olivier. So what we did, we pre-computed the critical case of Genoa about medio models, the models that you find listed there, so WRF in both the version, both cores, MesoNH, REM, Farm and Arome. And as manager of the site, of the portal, we upload them in this repository that we connect through the service. So as soon as today we will log into the portal, you can find here the menu for access the service. This portlet will show up for you. Here you have a set of the possibility to select several files about the critical case of Genoa, the one that we are studying in the school. We have, I think, between 20 and 30 files that can be served and visualized. So selected in that menu, you can choose one of the output, the one you prefer. For example, I changed every time the model I visualize in the presentation, just to give you an idea of which kind of files we have. As soon as you select the file, you see that here will appear all the parameters that are available and stored in the file itself, so all the variables present in the selected file, and you simply clicking on the name of the variable, you will visualize it. So I selected the specific humidity, and this is what show up when I consider MesoNH, the file MesoNH classified at the 7th. As you see, as soon as you select a parameter, several other information appears, the height, and we saw before that it is fixed at 2, since we decided to use this kind of convention. You see here that we are able to visualize the date these data are related with. Please note that the data that the dates that are presented are in bold, while the other are quite transparent. This means that we have the data for the 4th and the 5th of November 2011. And let's see. So further information related to data we are visualizing. I changed the model. This time I selected WRF IRW. Again, I'm visualizing the specific humidity. As you saw, you also in this case, the scale here appears together with these informations. And there is the possibility to change the opacity of the data. So, and to make video animation, let's say. Probably video is not the right word. So here you have the overlay opacity. You can change it. I changed file, I changed model, Arome this time. I selected 66%, before it was 100%, and you can see the transparency of the picture mapped on the map, geographical map. To make an animation, if you see here, you have these parameters. If you click on first frame, of course, I would suggest to move on the first date you have available to have a better animation, a longer animation. So you can select the first date you have available, and after click on the button first frame, and this you will see it will appear create animation. You do the same for the second frame. So you move on the second date, and you click on last frame. Yeah. And thus, in this way, you are fixing the limits of your animation. Simply clicking on create animation, your animation will start. And I think that it is almost all related with the visualizer because it is quite simple and quite intuitive to use. You can find here more information, more documentation about the tool, and this afternoon we will start in using the tools. If you have questions for both of us.
I have two questions. The first one is related to all the output variables that we can visualize and we can pass from the meteorological models to the hydrological models. Are these variables the only variables we can, that make sense that we pass to the hydrological models, or are just all the variables, output variables of the meteorological models?
No, there are a set of parameters.
And we can browse the whole output variables of the meteorological models and export them in case? Or we can export only the
Since the DRIHM project is compliant to the standard, the only output that you can retrieve are the ones that are compliant to the standard we decided to adopt. So let's say the P interface, the Q interface, and tomorrow we will see another. So no, the answer is not. Just the one that adopt the standard we decided.
Yeah, maybe I can add a little bit to that. That's also the priority for us at this moment, is making sure that the right data goes from meteorological models to the hydrological models. We have discussed the option to allow for native output of whatever model the model provides, but that's not fully functional yet, so that's why during this course we'll focus on these data sets. But if you would have like the WRF model can write out NetCDF, or most meteorological models write out data in NetCDF and GRIP file format, and you would be able to visualize it using some of these tools. But yeah, for today we focus just on these quantities.
I have a follow-up question. I was wondering why the rainfall accumulation variable when we want that is chosen as an output from the WRF, especially as an input to the hydrological model. I thought that would be one that would be useful.
Sorry, which quantity?
The rainfall accumulation output.
Yeah, the rainfall accumulation, I think that's what we refer to as LWE, thickness of precipitation amount. So that's effectively accumulated rainfall. But this is the standard name as in the CF convention. Okay, no further questions? Then we'll have a break.
Yeah.
Thank you.
Thank you.